Hello everyone. In the previous lectures, I explained the formation of a protostars as well as the formation of a protoplanetary disk. In the present lectures, I will explain the evolution of a protoplanetary disk. First topic is the young stellar object. Second topic is the evolution of a protoplanetary disk. First topic is the young stellar object. I draw the molecular cloud to a protoplanetary disk. Class 0 is a molecular cloud cores. So I explain the inside-out collapse in a molecular cloud. Typical size of a molecular cloud core I showed you in the previous lecture is a 5,000 AU to the 10,000 AUs. The materials is accreted at the centers to form a protostars, as well as a protoplanetary disk. In the class 1s, still some of the gases remains in the outer regions. The size of the disk is about a few hundred AUs. In these figures, you might recognize bipolar outflows, forming a disk around the protostars. This is a disk. If most of the materials is accreted into a protostars or disk, then stage is moved to the class 2. In this stage, we call the classical T-Tauri stars. You can recognize jets originating from the protostars compared with the class 1 stage, less dense environment. Some of the material is accreting to the protostars. We call that this disk is accretion disk, because the materials migrate to the central regions with the angular momentum. Then actually there is some way to release large angular momentum carried by a gas accreting onto a stars. Such a angular momentum is released by a jet. Then this disk is transit into the next stage of the class 3. We call that weak line T-Tauri stars. There is no jet. T-Tauri stars has several characteristics. First one is variabilities. It changes brightness in a few minutes to the 100 years. And also the T-Tauri stars show the presence of the lithium lines in the absorption lines. So this means the surface temperatures should be low, because the lithium is easy to be converted at the high temperatures, more than the 1 million kelvins. So lithium captures the proton to convert it to the heliums at 1 million kelvins. So this is a strong evidence of a young stars with low temperatures. The emission and the absorption lines is clearly shown in the spectral energy distributions, and both UV and IR excess. So UV excess show the high energy excess, and the IR excess show the low energy excess. So this is a spectral energy distribution. Horizontal line show the photon frequencies. Vertical line is a flux from T-Tauri stars. This region is a visible light. We can see only the visible light. We cannot see the IR or UVs. There is some reason why we see only visible light. One reason we can see the visible light is a visible light penetrates the atmosphere of the Earth. The other reason is that visible light is dominant in the spectral energy distribution. Then if you look at the classical T-Tauri stars, blue curves, you can easily recognize UV excess in the high frequency region, IR excess in the low frequency regions. Even in the weak line T-Tauri stars, you can easily recognize IR excess. Then now I'd like to consider the classical T-Tauri stars, weak line T-Tauri stars. Classical T-Tauri stars correspond to the class 2 object. Gas is migrated to the protostars. So during the migration, frictions between the gas molecules produce the heat. Heated gas emit the IR. Due to the heated mechanism by the accretions, we can explain the IR excess. The mechanism for the accretion of the gas two space shuttle is rotating around the central stars. Astronauts think two space shuttles need to be moved together. So he connects the two together. Then what happens? Actually, the attractive force is acting between the two space shuttles. Inner object is moving faster. Then the spring is stretched. Attractive force is acting between the two space shuttles. Outer space shuttle is pulled in this direction. So this means torque is acting on this space shuttle. Then angular momentum is increasing because of the torque acting on the outer space shuttle. Outer space shuttle is moving to the outer orbit. Inner space shuttle loses angular momentum, so it's going to move to the inner orbit. The unfortunate result is go to the very opposite directions. If you try to stick the two space shuttle together with the springs, two space shuttle is moving away from each other. So inner space shuttle is moving inner orbit. Outer space shuttle is moving outer orbit. So some of the gas might move outward, but some of the gas migrating inward. So this is a cause for the accretion of the gas. So because of this accretion of the gas, we call that this disk is accretion disk. Magnetic force has a crucial role to transfer the angular momentum outward, and the gas molecule migrate to the protostars. So gravitational potential becomes steeper, very close to the protostars. Then for the gas molecule falling to the protostars from the inner edge of accretion disk, UV might be emitted. Sometimes brightness is increasing, sometimes is going to be dark. So change of the brightness of a star can be explained by the sporadic fall of the gas onto the protostars. So in the case of the early stage of the evolution of the disk, excess of the UV and IR becomes significant. It indicates the active accretion of a disk. But this active accretion is going to be a slowing down, then transit to the weak line T-Tauri stars. In the late stage of the evolution of a disk, weak or no accretion of gas in a disk. Gas in a disk is heated by the light from central stars. Then the process of star's radiations, disk emit the light. Due to this process, we can observe the IR excess of the weak line T-Tauri stars. So we'd like to find out the transition from the CTTS to the WTTS. We could consider the two sources of the radiation from a disk. First one is the intercepted stellar radiation. Protostar emit a light. Some of the light is intercepted by a disk. Then disk is heated and they emit the IR. This is the excess of the IR. And the second source is the dissipation of the gravitational potential energy. During the falling process of a gas molecule to the protostars, potential energy is lost during the falling process. Then this lost potential energy is converted to the kinetic energies. So increasing the kinetic energy of the gas molecules increase the temperatures, excess of the infrared radiations. So there are two sources of the radiation from a disk, classical T-Tauri stars. Second source of the energy should be dominant. So this is a gravitational potential energy. This is the first case. If the second source of the energy, dissipation of the gravitational potential energy, is larger than the intercepted stellar radiations, we can expect CTTS. We could solve this equation to find that m dot. So m dot need to be the larger than 1.4 times 10 to minus 8 solar mass per years. So this is the condition for CTTS. If the mass accretion rate of a star is less than these values, this corresponds to the weak line T-Tauri stars, WTTS. Then I'd like to show the T-Tauri stars in the HR diagrams. In the previous lectures, I explained the Hayashi track. Vertical line correspond to the highest track. So depending on mass of a star, the different paths. Also I show the time scale. This is 100,000 years, 1 million years, 10 million years. This classical T-Tauri star is expressed by the solid black circles. So you can recognize solid black circle can be discovered in these regions. This corresponds to CTTS. An open circle can be discovered in this region and then WTTS. So as we expected, WTTS is older than the CTTS. Then after the WTTS, the star is evolved into the main sequence stars shown on the blue lines. Also, I show the spectral energy distribution for the CTTS. You can easily recognize large IR excess for the CTTS. So almost no IR excess to the main sequence stars. With the mass and temperature of the disk. Left figure show the vertical line is the logarithmic value of the mass of a disk. And the horizontal line show the energy flux at the wavelength of the millimeter wave. So it's longer than IR. If the energy flux with the millimeter waves becomes smaller, the mass of the disk is also decreasing. So you can find that the decrease in mass of the disk with the decreasing energy flux. The disk mass is less than the 10% of the solar mass, but larger than the 10 to minus 3 solar masses. And also we could find out the temperatures of a disk. Sublimation temperatures of H2O is about 170 kelvins. So this vertical blue line shows the sublimation temperature of H2Os. The lower temperatures, ice H2Os, and then gaseous H2O, higher temperatures. Temperatures at 1 AU is given by the T sub-bands. Some of the disk has a temperature is lower than the sublimation temperature of the H2Os. In this disk, water might exist as ice in the Earth's orbit of the 1 AU from protostars. So this disk temperature is higher than the sublimation temperature of H2Os. H2O is in the form of gas. I showed some observational results. So in these lectures, I explained the young stellar object from the class 0 stage to the class 1, class 2, class 3s. In the class 2 is the classical T-Tauri stars. Class 3 corresponds to the weak line T-Tauri stars. And the active accretions produce the IR excess. This is the end of this lecture.